Hello and welcome to video 39. This is problem number 5 in my review packet for the Honors Physics midterm this year. This is the most requested problem for me to go over, so I'm glad to indulge. The basic picture is sort of a storming the castle picture where you have some wall and we're then going to fire an arrow at some initial speed, which I'll call V0. And we're going to launch it at some theta, which is 30 degrees. And this problem you really want to break into two parts. The first part is going to be from when it's launched to when it gets to the wall. And the second part is going to be to where it lands. So perhaps I didn't do the greatest job of drawing that. You want the wall to be right at the apex because it's just barely going to clear that wall. And for fun, the floor inside of this castle is actually at a different height than the height it was launched from. So that complicates the problem a little bit. The key idea here, though, is that we're going to break it into a part 1 and part 2. And if you can understand everything that's going in this problem, you'll certainly understand anything I'm going to ask you in projectile motion and anything that most people would ever want to ask you about projectile motion. Sorry about that. The expression I like to teach people when I'm trying to show them about projectile motion is something I call no purple. What I mean by no purple is that you don't want to mix the x and the y components. So if we were to envision the x as being blue and the y as being, rather the other way around, the x as being red and the y as being blue, you have x things and you have y things. And there's a lot of information that students often confuse. One thing that's always going to be true in the x direction for a projectile is that it's not going to have any horizontal acceleration, at least as long as we're ignoring friction and things like that, which you'll always be asked to ignore in a freshman physics class. This acceleration is going to be 0. That's different than the acceleration in the y direction, which is going to be, assuming this castle is on the Earth, negative 9.8 meters per second squared. The other thing we need to consider is that this is launched at an angle. So that's going to mean that the velocity we have here is going to be different than the velocity in the x and the y direction. What I mean by that is that if I was to draw sort of an arrow of that, or vector arrow, I mean, not the arrow that we're firing, the x component is going to be some fraction of the launch velocity, and the y component is going to be some other fraction. So if this is theta and this is v0, the y component is going to be equal to v0 times the sine of theta, and it will always be the sine of theta because it's the opposite side of this triangle. That's the way we draw these. For the x direction, the velocity component in the x direction is going to be equal to that initial velocity, that magnitude, times the cosine of the angle. That's the way we're going to approach these. Generally, the first thing you want to determine when you're doing a projectile motion problem is the time of flight. Now, this problem having different landing heights, we're going to treat it as two parts, the first part and the second part. Let me go ahead and label this height. You're given that this is 10 meters, and that'll be important. And what I'm going to do is I'm going to look at section 1 first, so part 1 of the flight. Now the direction, if we want to figure out the time, is going to be the y component of velocity. So what I'm looking for is the y component of the launch velocity, so the part of this velocity that's going up that will just barely make it to a height of 10 meters. That's exactly the same question as if I took an object and threw it straight up into the air and wanted to know how much time it took to reach a height of 10 meters. So if you're looking at part 1 here, this is going to be the y direction, so I'll switch over to blue. And I'm going to make this the initial position and this the final position for the purposes of our calculations. And the equation that best suits us here, I would go with, personally, the VF squared equals V naught squared plus 2AD equation. Keeping in mind that this is just the y component of the velocity, not the whole velocity. We know that at the top, the velocity in the y direction here is 0. So this is going to be 0, square it if you wish. The launch velocity, which we're trying to figure out, let's go ahead and put a little y next to it to remind us that that's in the y direction, plus 2 times the acceleration, negative 9.8 meters per second squared on the Earth. If we're saying that up is a positive velocity, we have to say that the acceleration is negative. Those signs must match. If they didn't, if we had a positive acceleration and a positive launch velocity, that would mean the arrow would go into space, and NASA would be interested in that. The D here is 10 meters. So you bring the V naught squared over here, and you're going to get that the y component of the initial velocity is going to be, let's see, 19.6, 10, so it's going to be 196. Take the square root. You're going to get an initial y component of velocity that is 14 meters per second. So what do we do with that now that we know the y component of velocity? Well, there's a couple things I'm going to use that for. One of them is to get the time up. We know the final velocity is 0 in the y direction, and we now know the initial velocity is 14. So I'm going to treat this as if you had a rock or something, and you were to just throw it straight up, and this was the initial position, and we now know that the initial velocity here, I'll put the y so we keep it straight, equals 14 meters per second, and the velocity final in the y direction is going to be 0 meters per second, and we want to know how much time that takes to happen. So we're completely ignoring the fact that this is moving horizontally at the same time, and we're just focusing on the y direction. So the equation I would use here would be that the acceleration is equal to the change in velocity, or final velocity, minus initial velocity over time. So time equals final minus initial velocity. Sorry for jumping back and forth between V naught and VI. They're the same thing. Divided by the A. And when I plug in the numbers here, VF is 0. VI was 14 meters per second. The A, being on Earth, is negative 9.8 meters per second squared. And that's going to give us a time that is 1.43 seconds. So the time that it takes the arrow to go from launch to the top of the wall is 1.43 seconds to just barely make it up there. Now, we also need to consider the x components of velocity. And let's actually answer this first question, A. We sort of ignored it. We know, if I can redraw this picture again, that this must be launched at some magnitude, some velocity, or some speed. And we know that it has an x component, and we know that it has a, let me use the red, let me be consistent. We know that it has an x component, and we know that it has a y component of velocity. We've already figured out that this is 14 meters per second. We know that that's 30, so we can figure out from that the initial velocity. So Vy equals V naught cosine theta, or V naught equals Vy over cosine theta, because we have the theta. It's 30 degrees. So when you plug in the numbers, you're going to have 14 meters per second over the cosine of 30 degrees, 0.866, and that's going to give you an initial velocity, or a launch velocity, of 28 meters per second. Oh, wait a minute, I'm falling asleep at the wheel. For the y component, it's the opposite side. We're going to use sine. These will be sine. So it's going to be 28 meters per second is the launch velocity, and as long as we're here, let's figure out the x component of velocity. The v0 in the x direction is going to be v0 times the real cosine of theta, which is going to be 28 meters per second times the cosine of 30 degrees, or 0.866, and that's going to give us an x component of velocity that is going to be 24.2 meters per second. So let me just fill in a couple things that we've answered already. The launch velocity must be 28 meters per second. I'm going to come back to this question because it's an energy question. And let's analyze this situation further. So we now know that it takes 1.43 seconds to go from launch to the top of the wall, and we know that it's launched at 28 meters per second, has a horizontal velocity of 24.2. We now need to look at section 2 of the motion. So when it goes down from here to here. This you can treat like a horizontally launched projectile problem, which is significantly easier than one that's at an angle. This, you're told, is 5 meters. So we want to calculate the time too. This is actually the same as the amount of time it would take if you started here, and this was your initial position, and this was your final position, and you fell some displacement that was -5 meters. And to figure out the time, probably the easiest equation to use again would be d equals VIT plus 1/2 AT squared. I would plug in the displacement, -5 meters. The initial velocity is now 0 at the top. Plus, again, the acceleration is -9.8 meters per second squared times t squared, or t equals 5 divided by 4.9. Take the square root. That's going to give you a time that's loosely 1 second, but let's round to 1.01 seconds. And this is going to be t2. So we now know the time to go up, 1.43, and a different time to go down, 1.01. A very common misconception is that this time down is always the same as the time up. That's only true if you're landing at the same height you were launched from. But this is one of the more complicated kinds where it starts at one height and ends at another, which is why I like to ask it. Because if you can understand this problem, you can understand any of them. So I ask you, how far does it go from the wall to here? How far past the wall does this land? Well, it's really asking you for the range. Range sounds an awful lot like distance in the x direction, and it is. So we're going to use distance equals initial velocity times time plus 1/2 AT squared, also known as the range. And the initial velocity, you have to be real careful here. A lot of people want to put in 28. It's not 28. It's the x component of 28, which we found is 24.2 meters per second. Now, since we're only talking about the distance from the top of the wall to here, we're not going to use the whole time. We're only going to use the time once it got past the wall, which was 1.01 seconds. Now we're going to avoid another misconception, which is that the acceleration is always -9.8. Well, the vertical acceleration is -9.8, but this is in the x direction. You don't want to mix the blues with the reds. You don't want to make purple. So this is actually +0. And when you multiply those together, you should get essentially 24. But when you put it in, you'll get 24.4 meters. That is how far the arrow travels past the wall. By the way, it wasn't asked for it, so this was part 2. On part 1, if we wanted to do the same thing, you would have had the same horizontal speed, 24.2 meters per second, but it would have been times the longer time of 1.43 seconds, which means the arrow must have been launched a distance of 34.6 meters away from the wall. That wasn't asked, but it's fun, so we answered that too. So this winds up being 24.4 meters. And as far as the vertical velocity, when it strikes the floor, you have a couple ways you could do that. One, by the way, you're definitely using the y direction when it comes to vertical velocity. So let me draw a picture here. So the arrow is doing this. I should say it's doing this, coming back to a height that's less high. Couple things. One, you got to keep your components straight. So instead of thinking of this as being 28 meters per second, it's not. It goes up at the y component of velocity, which is 14 meters per second. I'll get a lot of students here that will say, oh, I know that. That's down at 14 meters per second. True if the arrow made it all the way back to the same height, but this is at a different height. This is at only 5 meters. Now, since we've already done a lot of work on this problem, we've seen that the time to come down from here to here is 1.01 seconds. So that's what I would use to calculate the velocity, because we know the velocity in the y direction here is 0. So I would just use VF equals VI plus AT, where VI is the 0 at the top here, times the acceleration, negative 9.8 meters per second squared, times the time, which is just the time from here to here, or 1.01 seconds, and that's going to give me a final velocity of essentially negative 9.8. Let me go ahead and plug that in. 9.9 meters per second on the way down, which is slower than it was launched at. The reason it's slower is it hasn't had enough time to increase its speed to the point that it's traveling just as fast as when it was launched. So we've now answered that, and that'll be negative because it's going down 9.9 meters per second. The horizontal velocity of the arrow when it strikes the floor, there's no calculation necessary for that. There's no acceleration in the horizontal direction. So the horizontal velocity stays 24.2 meters per second the entire flight, or at least until it hits something. So the horizontal velocity is just 24.2 meters per second. And if we're going to figure out the angle it makes with the ground, that's really a vector problem. A pretty simple one. But you've got an x component of velocity of 24.2 meters per second plus a y component of velocity that's going down at negative 9.9, or the arrow shows down, so I'll just write it as 9.9 per second. And then this is the resultant. So if this is the angle that you land at, this really just becomes a trigonometry problem. So if you want to get the theta, you can see the 9.9 is the opposite side, and this is the adjacent side. So the tangent of theta is going to be equal to the y over the x, and that's pretty much what it always is. So if you take the inverse tangent of 9.9 meters per second over 24.2 meters per second, you're going to get a theta that is 22.2 degrees. So 22.2 degrees from the horizontal, or 22.2 degrees south of east, if you like, as I drew it. But that is going to be the direction. To get the magnitude, it's even easier. That's the Pythagorean theorem. So 9.9 meters per second squared plus 24.2 meters per second squared. Take the square root of that, and that's going to give you the magnitude of your final velocity. And that is a final velocity that is 24.4. And it makes sense that it would be a little bit bigger than either component. But you get 24.4 meters per second. And then the last thing I threw in here is just this question about an arrow with an effective spring constant. How far, or what is the spring constant of the bow? For that, you need to know the mass, because that'll be related to the energy. And what we're saying here is that if we assume all of the spring potential that was in the bow, which if you remember is 1/2 kx squared, all of that potential energy went into the launch velocity, meaning the magnitude of launch velocity, or the kinetic energy, which is 1/2 m times the launch velocity squared. We're going to cancel out the halves, or as I like to say, have-nots. For those of you still listening 22 minutes or 20 minutes into a video. But the k is what we want, so if I take k, that's going to be equal to m times v0 squared over x squared. Or plugging in the numbers, the mass is 1 kilogram, which is fairly beefy arrow, times the launch velocity, the entire launch velocity, the 28 meters per second, not just the components, don't forget to square, divided by the distance that it was stretched, which was 0.5 meters. Square that, and that should give you a spring constant that is 3,136 newtons per meter. Don't forget, when you're doing things like this, make sure you write out the equation with nothing plugged in. Ideally, arrange for the variable you want ahead of time. Show the substitution with the units and have a final answer with the units. So let me put this up here. This is a fairly lengthy projectile motion problem, but like I said, if you understand this, you will understand everything. The big concept is that you want to take the time up and treat that differently than the time down. The results of your kinematics equations at the end of the first part feed your kinematics equations at the second part. Don't mix the x's and the y's, don't mix reds and blues, don't make purple, and you should be fine. Hope this helps.